Hi everybody who is watching this video. I am Sir Olenjolai Single from United Republic of Tanzania. I would like to welcome you into this fantastic lecture, which is sessions, or we call it period of lecture 4 for gravitational mechanics. So I believe that you have been going through the lecture 1, lecture 2, and lecture 3 of gravitational mechanics. So today I would like just to take you further into the first lecture, when we are going to do some examples or problem solving. So what you've been learning, let's say from lecture 2 and lecture 3. So we used to do just computations after deriving the formulas, but we haven't done it and see how questions are being asked. So in this lecture, I would like just to tell you that we are going to cover that. And in case that this is your first video that you are watching, then I would like just to ask you that please, you have to watch the other previous lecture or other previous session 1, 2, and 3. You can find them in the YouTube channel that's called Tanzania Online A-Level Secondary Schools, Olenjolai. Thank you also if you have subscribed. I believe that you have subscribed so you get the notifications and information about any new lecture that we upload in this YouTube channel. So today we'll be proceeding with periods of session 4, which actually we are going to concentrate on problem solving, because it's better if we solve some problems in order to test our previous understanding, if you have understood the concepts or not yet. But before I go to the session 4 or period 4, I would like to give you the quick review of what you've covered in lecture 3. So in lecture 3, basically the subtitle, it was called the applications of Newton's universal gravitational law. So that's what you've learned. So the first applications we learned about how we can deduce the formula for mass of the S, and then we made the computations and found that the mass of the S is what is 6 exponent what? 6 exponent 24 kilogram. And then we learned how we can find the density of the S, derive the formula. I taught you how to derive the formula and how to find it. And then in our finding, we have found that it's 5.5 exponent 3 kilogram per meter cube. And then I taught you how to find the mass, or to derive the formula for the mass of the sun. Okay? Mass of the sun is how do we derive it. And then I taught you how we can use the universal gravitational, or Newton's universal gravitational law, to find the acceleration, to derive the formula for acceleration of gravity, which is G, and then we found, which was 9.7 meter per second square. Again, I left the homework that you have derived an expressions for G, right? I believe you did it. So I think that you have got it. And let me just give you the response of what you should get at the end of your computations or at the end of your derivation. Okay, because they've been asked that the questions will say derive an expression of acceleration of gravity at the S's surface in terms of radius of the S and density of the S and G. Okay, so because it's just like a repetition of what I've taught you, I don't think if I'll be, but anyway, I think that's better if I do what? I do corrections, so for you to be sure whether what you found is correct or is not correct. Okay? So let's say correction, let's start with correction of 40. Corrections of homework. Homework, what it was, homework 3. Okay? So the first step, we go straight forward to the solution of that problem. The first step, we say that consider a body of mass m, and this body might be a planet revolving around the Earth. Around the Earth. So then, this is what you have to say. So this is circular path, and then we say that This is the body revolving the S. Here we have mass of the S, and then here we have mass of the body, and this is its own orbit. And here we have radius of the S. Can use either, but because we have been given the symbols, so we've been given R, capital RE. Okay, so this is the orbit, and this is the S. Right? So this is the S, and this is the body of mass M. Okay, so you can draw your cycle clearly. Okay, for me, I just sketched it for you to have a concept. But you can use any ring structure or any circular structure to draw properly your cycle. So the second state now, we say that we have to recall the mathematical equation, the mass equation, mathematical equation of Newton's universal gravitational law. And that formula is saying that the force of attractions between the two bodies in the universe is directly proportional to the products of their mass. So here you have two news that we say that we have the mass of the body, which is attracting the S, and also the S is attracting, is being attracted by this. So this body is attracting the S, and the S is attracting what? The mass. And this force of attractions we call it F subscript of A. Okay? So you say the mass of the body, then multiplied by mass of what? Mass of the S, divided by radius of the S square. Okay? So this we call it the first equation. The second state, I told you that for this body to be in a constant path or in the same path, we say that the weight of the body, this body M, should be equal. Should be equal to the force of attraction. So it means that the weight of the body, not angular velocity, the weight of the body is equal to mass of the body times gravity. Okay, so this is equation 2. So from this condition that the weight of the body should be equal to the force of attractions, so it means that we equate equation 1 and the equation 2. So if you equate, we get mass of the body times gravity, gravitational constant, the mass of the body, then mass of the S over radius of the S square. Right? So then it's mass of the body cancel. So we have gravity is equal to universal gravitational constant times mass of the S over radius of the S square. Okay. So that's the case. And then if this is the case, what do we say? We say that, okay, fine. That the expressions for it for gravity. But according to the questions will say derive an expressions of acceleration gravity, G it means, at the S surface in terms of radius of the S and the density of the S and the gravitational constant. So according to the questions, we will be given that RE, we have to say that it is RE, according to the question. So it means that acceleration gravity is equal to universal gravitational constant, mass of the S, and radius of the S square. So this will be the third equation. Again, we go for the first state. So the first state, we say that recall the concept of what? Concepts of density in Form 1. So you have learned about the density of the body, and what we have taught you, we told you that the density of the body is equal to the mass times 30 mass over volume of the body. So if you are looking the density of the S, then the density of the S, for that case, which is this one, density of the S is equal to mass of the S over volume of the S. But the S, the shape of the S, right, is what is sphere. So because its shape is sphere, so we say that the volume of the sphere, this one is equal to the volume of 40 of sphere, which is 4 over 3 pi r of the S cube. So therefore, we say density of the S is equal to mass of the S over 4 over 3 pi r of the S cubic. So if we see, this is question 3, question 4, but there's a relationship between question 3 and the question 4. What is the relationship? The relationship is here. Here we have mass of the S numerator. We also have mass of the S numerator. So you can make this a subject and then we'll come and substitute here. Right? If you understood, if you have a question, please ask in the comment section. So then this is over 1, the cross multiplication. Then we have 4 over 3, density of the S, pi r, radius of the S cube, is equal to mass of the S, and this will be equation 4. Right? I believe you enjoy the beauty of physics, and especially the beauty of gravitational mechanics. So if that's the case, we go for the 50th step. In 50th step, we say that substitute equation 4, substitute equation 4 into equation 3. So what do you get? So you say acceleration gravity G on the S surface is equal to gravitational constant. Instead of the mass of the S, we substitute this 4 over 3 pi radius of the S cube. Yes. And then divided by what? Divided by radius of the S square. And then you have density of the S here. Just for the density of the S. Okay. So if that's the case, acceleration gravity is equal to 4 pi radius of the S, because we simplify this and this, and then gravitational constant, density of the S, that is density of the S, and then we say that over 3, we have 3 here, over 3. Okay? So that the formula required to be driven in order for you to get the marks of this question. So that the formula of the formula of acceleration with the gravity of the S surface in terms of density of the S, gravitational constant, and radius of the S. So understand. So all of these 3 other are the constant. 4 is constant, pi is constant, 3 is what? Is constant. Okay, so that is the corrections of the work that I left it to you, so you can check your work. If you are right, congratulations. And I just congratulate you and encourage you that keep on doing it. And then if you fail to get the right response, like what I derived there on the blackboard, don't worry. That is what happened in case that you are learning stuff. So if you tried, that is fine. If you didn't try, I'm very sorry for that. So let us start this. This will be example 2. Example 2. The mean radius, say the mean radius. The mean radius of the orbit mean radius of the orbit of the Halley's comet. Of the Halley's, this is the one of the comets. One of 14 of the comet is 18 times longer than that of the S. Of the S. Calculate the time of the Halley comet. Of the Halley's comet. Add the question. So the question states that the mean radius of the orbit of Halley's comet is 18 times what? Times longer than what? The S. Calculate the time of the Halley's comet. Means to complete one revolution around the sun. That's the question. Read it clearly, read that question carefully, and then use the previous concept. The concept required to answer that question we've already covered in lecture 1, or either lecture 2 or lecture 3. So that's why I have put it there. So Halley, don't trouble yourself at what the means of Halley. Halley is a new vocabulary. This is just the name of the comet, right? So the mean radius of the orbit of the Halley, the mean radius of the orbit of the Halley is 18 times longer than that of the S. Calculate the times of the Halley's comet. Means that the times of the Halley's comet to complete one revolution. So it's not a tough question. You have just to understand. Solution. Let us go to the first step. Let us analyze the data we've been given. The data being given is that the mean radius of 40 of the orbit of the Halley's comet is 18 times longer than the S. So here we have to let the mean radius of the S to be equal to RE, right? And then so be given the mean radius of 40 of orbit of the Halley's comet is 18 times. So then we say that the mean radius now of the Halley comets, this is equal to 18 times radius of the S. Okay? Calculate the time of the Halley's comet. So what is required? The period. Means that calculate the times for the Halley's comets to complete one revolution. So what is required? It means the period of Halley. So this is required. Do you know what it's why is it required? Why do we call it a period? Because the Halley comets is actually revolving the sun in its own orbit. And when it completes one revolution, then again it goes the second revolution, third revolution, fourth revolution, fifth revolutions. So it keeps on repeating the same process. Okay? So how do we deal with this problem? Go for the second step. The second step, we say that, okay, we have our data, we have mostly all the details. Let us refer what we know in case of gravitation. So I told you about, so we said that we call Sandy Kepler's. Sandy Kepler's, so we have to recall Sandy Kepler's mathematical equation. Mathematical question. So how does it is it? Kepler said that the square of the period of the body that revolves in the universe that revolves around the Earth, this one will be proportional to the radius of the radius. Okay? It's directly proportional to the cube root. No, it's directly proportional to the cube of 40 of radius. Are we together? So we say that if this is the case now, T is equal to K in R cubic. So divide by R cubic, divide by R cubic. So we have T square of R cubic is equal to K. So means that K, we can calculate this value of K by the periods of Halley if we could know it. Of a radius of 40 of Halley. And also you can calculate the value of K by taking the period of the S square over radius of the S cube. Okay? So if this is the case, we say that this is equation 1 and this is equation 2. What do you see there? Yeah? What do you see there? You see that the two expressions are equal. Our interest, we want to find the periods of Halley. So we say that this is the first step. Third step. So I said the same, we said that take question 1 followed by question 2. Or we said that take question 1 is equal to question 2. So equate, right? So if that's the case, we say that the period of the Halley square, the radius of the Halley square, no, Halley cubic, sorry. This is S, radius cubic of the S. So where did he get these formulas? So I took this equation, I equated with this. Right? So when you equate, what are we looking for? We are looking for this one. So he said that the period square of Halley will be equal to period of the S square, radius of the Halley, radius of the S by 20 cubic. So we say that period of Halley right now to be square root of what? The period of the S square radius of Halley of what? Radius of the S cubed. So if you square the periods of S, if you find the square root of periods of the S square, then you get period of S. So we say the period of the Halley is equal to period of the S and square root of radius of the Halley, radius of the S, R3. Okay? And what will be the period of the S? 1 year. Period for the S to revolve for system. Radius of the S is 6.4 meter. Right? Then you have radius of Halley, it is multiple of that ones. But you need period of 40. E is equal to period of 4. Period of the S. Period of the S. And this period of the S is 1 day. And 4 hours. Right? And then we have 24 multiplied by 60 divided by 60. Okay? This will be seconds. Huh? Hour. Okay, this is just I was doing for 1 day. Excuse me. Period of the S. I didn't finish this sentence, let me finish it properly. Then we get the periods of the S to revolve. The sun is 365 days, or 1 year, or 12 months. So period of the S is 365 multiplied by what? 4 hours. There are 60 to convert into minutes, and 60 into seconds. Right? Okay. Or even if that is in case of 40 seconds, you want to express everything in seconds. But because this Halley also is going to have a period, so you can say period of the S So it's a period of the S, you can even use 1 year, it's fine. Because you're not limited from the question. So it's that the period of the Halley is equal to the period of the S. Time short. Guys, we are looking for the periods of the Halley. It is the period of the S is equal to 1. Is it 1 year? Period of the Halley will be, remember that from this formula. Period of the Halley is equal to the period of the S, then square root of 40. Radius of the Halley over radius of the S. This is what? Cubic. Right? So if that's the case, we say that period of the Halley is equal to period of 40 of the S, which is 1 year. Right? Or it's more than that. 1 year. Then we say that multiply by what's the radius of the Halley there? 18. Radius of the S over radius of the S cubic. So radius of the S and radius of the S cancel. So period of the Halley is equal to what? 1 year. Times what? Square root of 18 cube. Right? So you have to use your scientific calculator and then find that it's 76.4 years. 76.4 years. For the comets to complete one revolution. So it's 76.4 years. So the year had to evolve until it finishes and then waiting at the time that when the comets will be complete this motion. So therefore we say that, because the questions was asking what? The time of the Halley's comet. The time of the Halley's comet. So you say that is what? 76. Point what? 76.4 years. You are done. Right? Okay. That is good. Believe that you still enjoy this song. So let me give you the example. So what will be what will be the acceleration due to